Next topic I expect to be one of the most interesting for you guys. It's a typical PD phenomenon identification. First, we will speak about the phase-resolved PD pattern and the polarity. And then we will go into each single major PD phenomena we find normally in rotating machine. And we will see what are the characteristics of the pattern related to each, to the phase-resolved PD pattern related to each defect. First, PRPD pattern for us is the key, always. In the PRPD pattern, we normally put the pulse amplitude, the pulse polarity, and the phase angle. These information, they are, let's say, the only way we have to recall the physics of the phenomena. The applied voltage is the engine of the PD. If we don't have the applied voltage, we don't have the PD. And the correlation between both applied voltage and partial discharge phenomena is the one that will give us the tools to carry out the phenomena identification from the PRPD, phase-resolved PD pattern. We start with the voids. Normally, in generator, in motors, we have a system of insulation made with normally, recently at least, with mica. And even if we have a very strong, even if nowadays there is a very strong vacuuming during this process, we still have some voids present in the generator. These voids will have a very characteristic pattern with a symmetry between the positive and negative pulses. We will have a regular phase interval, and we will have a low magnitude at this stage, and also triangular shape. I forgot to mention it before, sorry for that, but I think I need to point out this thing. Rotating machines are designed not to be PD-free. They are designed with materials and technology to withstand partial discharge. So 9 out of 10, if we test one generator, we will always find some kind of partial discharge phenomena. It's pretty common. The important thing in this case is to identify such phenomena and check it along the time. So PD in a rotating machine is not as bad as PD in cables, for example. The insulation material in this case is designed to withstand such PD stress. Going on to the typical partial discharge phenomena, we have also embedded delamination that we can say is a second stage from the microvoid. So we have delamination that is inside the insulation, not on the boundary sides with the metallic part, but in the middle of the insulation. Such phenomena always give us a phase-resolved PD pattern that is very symmetric. We have large phase angle intervals. When I mean phase angle, I mean the phase angle range that is covered by partial discharge activity. We have a mostly triangular shaped pattern, and we have a markedly start before the zero crossing of the voltage. When I speak about zero crossing, I mean when the voltage is zero. So in the PRPD pattern, we are talking about angle equal to 0 or angle equal to 180 degrees. Another kind of delamination is localized between the insulation and the copper bars, the conductor side delamination. In this case, the pattern is characterized by an asymmetry. We have higher negative PD pulses respect to the positive one. We have a quite regular phase angle. There is an imbalance in the magnitude, and the phenomena can start before the zero crossing as well. The very important thing is the asymmetry respect to positive and negative pulses. On the contrary, when we have slot side discharge, so between the insulation and the stator frame, we have very clear positive PD pulse majority respect to the negative PD pulses. We have a quite regular phase angle interval. There is, of course, an unbalanced magnitude, but reversed respect to the conductor side delamination. The PD normally starts before the zero crossing. And one particular thing is that if you look at the PRPD pattern, is it triangular shaped, but we have that the highest PD values, they occur close to the zero crossing and not as a regular triangle in the middle of the phase angle range. Another phenomena we have normally, it's the stress gradient discharges. So we are talking about the portion of the generator when the bars come out from the stator core and they have a bending, and we have some stress gradient taping to decrease the electrical field. We have normally a higher positive PD respect to the negative PD pulses. We have a quite regular phase angle interval. The shape of the pattern is more rounded compared to what we've seen till now. And they are very, let's say, very easy to find in air-cooled turbo generators, for example. One of the last phenomena is not exactly an insulation defect. We are talking about bar-to-bar and bar-to-ground discharges. They occur in the overhang of the generator between the bars and the pressure finger, or between the two bars. These PD occur in the air. In fact, actually, they belong to the Corona family of PD, and they are characterized by very regular behavior between positive and negative. We have a super high repetition rate of the PD, so we have many of these events each second. Normally, the minimum values of such PD is far from the trigger level. So if you look at the PRPD pattern, there is a gap between the minimum value that we can detect and the minimum value of the PD phenomena. Last, very characteristic squared phase resolved PD pattern. We have normally a couple of square, one negative, one positive, with a 180 degrees phase angle difference, and characterized by rectangular shapes. These were the major PD phenomena and related phase resolved PD pattern. Obviously, when you go on site and you make the test, you can always find a mix of these ones, overlap of these ones, and it's important to carry out a proper data analysis. To carry out a proper data analysis, the first step is to identify and remove the noise occurring in the generator measurement and the eventual face-to-face crosstalks. We will see what are the normal classic rotating machine noise and disturbances issue. We will see in particular the exciter and electronic system noise. Then we will see a solution for such noise like the hardware filtering. And later on, we will introduce the Tekin patent about time frequency map filtering. That is a more customized solution. So what are the rotating machine noise and disturbances we can have during normal partial discharge testing? We can identify unsynchronized disturbances. Those came from the environment. For example, we have crane excitation, power tool operation, and so on, or synchronized disturbances. What I mean by saying unsynchronized and synchronized disturbances. When I talk about unsynchronized disturbances, that means that there is not a regular correlation with the applied voltage. So, for example, in the phase resolved PD pattern, I won't have triangles, group of points, like for the PD phenomena, but I will have flat response of signals all along the phase angle, or sporadic random points here and there. That is the unsynchronized disturbances, and they can cover what I want to see. Instead, when I talk about synchronized disturbances, I mean signal that is correlated with the applied voltage of the generator. That can come from a PD source externally to the asset. That can be due poor electrical connection. If we have some floating parts, for example, they can affect the measurement as well. All these kind of things are, let's say, very uncomfortable to be brought inside the acquisition. So if possible, it would be nice to remove them. And in this case, we take advantage of the phase resolved PD pattern to recognize the voltage correlated signal, to identify the PD correlation with their own phases, with the source of the PD, and to identify crosstalk signals. Very classical noise during acquisition is the exciter noise. If you see the pattern here, we have a group of 6 vertical lines, very, very stable and very, very precise. Those are basically covering something else. They are mixed with something else. I can say at first sight it is an exciter noise, and I guess that you can see as well the characteristic of vertical lines. But why it's so clear that is an exciter noise to me? Because normal PD, they are due to the physics. We have an applied voltage that activate and deactivate a defect. So there is a correlation with the phase angle and the change. In this case, these vertical lines, they cover a very, very narrow angle range, and they are very, very regular. Why? Because they are artificially, they are clocked. There is a clock on the exciter giving such disturbances, normally from the insulated gas bus transducers of the exciter, and we can find them very often. Very good thing for us, this signal frequency spectrum is normally far from the PD signal frequency spectrum. So we can easily identify them and get rid of them and separate the sources with the, for example, with the TF-map technology that will be explained a few slides ahead of us. Thanks to this time frequency map separation, we can identify properly on the black cluster the exciter noise, on the red cluster the PD phenomena together with the background noise. We can further investigate then this second PRPD pattern. Now, we can use also hardware filter to remove noise or unexpected signals. We can remove low frequency disturbances with the high pass filter. We can remove high frequency disturbances with low pass filters. We can combine these two and get a band pass filter, or we can attenuate the existing signal as well with an attenuator in case we have a very high signal and we need to understand what's going on. Here we have a case with a full acquisition where we have a PD and exciter noise together. If we make this signal just pass through our hardware high pass 2.5 MHz filter, the signal will be more clear. We have lost the frequency component coming, the frequency component belonging to lower than 2.5 MHz, sorry, but we will have all the rest very highlighted. This is very important, in my opinion, if you want to correlate amplitudes. We shall measure the proper amplitudes, not the exciter amplitudes. Then, the main topic for the denoising is a time frequency map. Basically, the time frequency map takes advantage of the information we have in the waveform, in the pulse waveform. Normally, the just two information we got from the pulse is the amplitude and the phase angle. And we create the PRPD pattern with these two parameters. But we can study the same pulse as per its spectrum. We can identify what are the what is the frequency spectrum of the pulse, and we can try to translate this analog information into mathematical numbers. That was the TF-map technology introduced by TechImp. We have one pulse. This pulse will be analyzed on board of the instrument. With the pulse amplitude and phase angle, we will build the phase resolve PD pattern. But with the rest of the information, so the waveform shape, we will study, thanks to a fast Fourier transform formula, an equivalent frequency and an equivalent time length. As I told you, it's not this the object of this webinar, but to make it short, with the time frequency map, we are able to see the signal from another point of view, and we can introduce filters and customize filters on this basis. We have a clear example. We have a full PRPD pattern when we cannot recognize any of the patterns seen before, but its TF-map signal is characterized by a low frequency signal and a higher frequency signal. We can decide to remove from the acquisition, to customize a TF map filtering just by drag and drop a square over it, and we will get the filtered data related to the PD phenomena. We get rid of what we don't want to include in our acquisition, and we make the PDA signal evident and spotlighted. Now we have seen basically what are the sensors, how we can acquire data, and how we can filter noise. We will see now how we should analyze data. To analyze data, we have to keep in mind a flow of action. First, we have to take into account the acquisition parameters. Then we can apply, if we want, some filter with the TF map. And as an output, we will have data set. These all activities carried out during the acquisition. We go back in our office, we go back to our laptop. We can still apply some more time frequency map separation, and we can study the phenomena one by one and trend such phenomena along the time if we have more than one PD measurement campaign for that generator or motor. So the PD analysis actually starts during the acquisition. We have to keep into mind that a very good data set will give us very quick and high quality analysis of the PD. What we should provide to the analysis is high amplitude PD signals data, lower amplitude PD signals data, machine working parameters like load and temperature, as suggested by several standards. We can take information about temperature of the generator and load to make an evaluation of which phenomena are going on together with the PRPD pattern identification. It is also suggested to use different time lengths to acquire the data during the acquisition, different pre-triggers values, and to use hardware filter as well. Whenever I'm doing the trainings to our customer, I always say them that data is free. Once we have everything connected, we have to, let's say, acquire the highest amount of information that we can by changing the acquisition parameters, by changing the filters, and if possible, by taking the measurement in different working condition of the generator or the motor. Here we have the same step. Suppose that we are on site during the acquisition. I can have this information during the acquisition in streaming that we have lower frequency signals and higher frequency signals, and I can acquire the whole data first. So I will have the acquisition on the left saved in my data set. Then I will apply the TF map filter and will acquire the PD pattern present on the right. Both shall be anyways saved in the dataset, because the dataset should include everything: different foot scale, different trigger level, waveform acquisition, presence or not of hardware filters, and presence or not of software filters. When I am back home, I will have, let's say, 20 or 30 or 40 phase resolve PD pattern to be analyzed, and I can take this information and use them for my diagnosis. The idea that I always try to bring into the customer mind is that whoever is analyzing the data should be able to recognize each step of the acquisition. So first we have noise and so on, then we start to identify one of the noise, we filter it out, we make a new acquisition. This flux of information should be, let's say, evident to the analyst, not just to the acquisition, not just to the testing engineer. Now we have our data set saved, we are at home studying the data, but we can still take advantage of the time frequency map. Even on the acquired data, we can take clusters from the classification TF map and study the related single sub pattern. And this is very typical in generator, because normally we will have more than one phenomena or crosstalk occurring in the same detection point. We shall be, let's say, good enough in the acquisition to have something to study during the analysis, thanks to the TF map separation. Last point is the identification of the single phenomena. We were able to, let's say, acquire the data properly. We have removed the noise. We have separated the sources. For example, in this picture, we are studying the red cluster signal only. We are marked on the red cluster. And we should be able to identify the phase-resolved PD pattern. This can be done, obviously, by a visual identification made by the operator. Our software also provides identification tool that is delicate, is not, let's say, 100% perfect, but if we refine the data properly, can give us a very good indication. Last, we should study the data along the timeline of the generator. It occurred to me in my career to test generators from the beginning of my career till now, where we are seeing always the same partial discharge phenomena characterized by very same amplitude and very same repetition rate. The phenomena is not evolving. In other cases, we have seen that along in 1 year, the PD phenomena increased and doubled its magnitude and doubled its repetition rate. So it was that kind of information that triggered more the attention respect to a stable high-level PD phenomena. The growth of the PD phenomena means an evolution in the defect that can be very harmful for the asset. Normally, the idea is to use the PD diagnosis of the monitoring. Let's say every 3 months, every 6 months, we have data and we compare the data with the old ones. We try to recognize the same phenomena. In case we see an evolution, we trigger the asset management attention to spotlight on particular phenomena. This can be, let's say, brought into a maintenance action or into a visual inspection to find out what's the issue and if there is a necessity of any maintenance intervention or even rewinding.